Alright, so this is the last, lecture 4, the last chapter of the energy unit. And this should be a nice little short one. Just want to point a few small things out and then we can be on our way. We'll be talking about energy diagrams and stability of equilibrium. That will be the biggest part of this. But I do want to start out just briefly with a little bit about the relationships between potential energy and force. So we know spring potential energy is equal to 1/2 kx squared. No surprise there. Now, remember, when we're dealing with potential energy, that potential energy is also equal to the integral of force with respect to the displacement. We've talked about that in the past. So if that's true, that means that force is equal to the derivative of potential energy. And as I mentioned in one of the videos, again, usually when we're doing this, we're dealing with spring potential energy, and this is no different. So if force is equal to the derivative of potential energy, then here's our potential energy equation. Let's see what happens if we take the derivative. So if I take the derivative of 1/2 kx squared, the 2 comes down in front, and that's really all you do. You've got 1 less in your exponent then. So the derivative of potential energy is going to be equal to the 2 and the 1/2 cancel out then, kx, which is equal to force. And that should come as no surprise, because what have we already learned? Spring force is equal to negative kx. So as you can see, and as I pointed out in the last video, and probably 1 or 2 before then, all of physics is just a big circle. These equations come from each other, and they're made by each other. Last time I showed you how energy equations are how we actually get that time-independent velocity equation. And this is no different. It's all connected, folks. Even the calculus, believe it or not, as much as we dislike it. So, of course, the negative comes from the fact that your displacement is always opposite the direction of your spring force. But yeah, just thought that was kind of interesting. So what this means then, of course, too, is that if you're dealing with this graphically, that the slope of a potential energy versus distance graph is going to be equal to your force, your spring force. Okay, on to stability of equilibrium. Here we go. We've got 3 scenarios we're going to be looking at here. The first is stable equilibrium. Stable equilibrium would be represented by an object at the bottom of a little dip there, kind of in a valley, I guess you could say. And it's stable because if it moves either way, it's going to return back to that original equilibrium position. Now we also want to make sure we're aware of what happens to potential and kinetic energy under these conditions. On the horizontal axis, we'll put displacement. On the vertical axis will be our energies, potential and kinetic. So as far as potential energy goes, when this object is at the very bottom here, it's at ground level. And if it's at ground level, it has no potential energy. But as it gets further away from that position and climbs, then your potential energy, of course, would increase. So you'd have that sort of graphical relationship. As you get further from the 0 point, you get a higher elevation and your potential energy grows. Kinetic energy, no surprise, is going to be the exact opposite. Because as you get further and further away from this middle position, what ends up happening is your kinetic energy is going to decrease. If you're moving here and it starts to go up, it's going to slow down. That kinetic energy is going to get smaller as it gets further from that position. Of course, at the very middle, this is where its speed is going to be the greatest, because it's flying down here, picking up speed, maximum speed right there, and then it'll start to slow down thereafter. So that's stable equilibrium. What do you suppose is next? Unstable equilibrium. So unstable equilibrium is basically like an object on the top of a little hill. It's unstable because if you nick it one way or the other, it's just going to fall down that hill. So let's just fix our energy diagrams here, because this will be different. So at the middle point here, we have ourselves a load of potential energy, because it is as high as it's going to be off the ground in that position. And as it goes away from that equilibrium position, as its distance or displacement x increases, you're going to get closer and closer to the ground. Your potential energy is going to decrease. So the graph will look something like this. Highest potential energy is when it's at the exact middle, at x equals 0. Kinetic energy is going to be the exact opposite. Now kinetic energy gets to be the smiley face. The reason for that is because as you get further and further from this position, the object is going to pick up speed. And if it's picking up speed, it's going to have larger and larger kinetic energy, which is what happens on this graph here. As the distance gets further and further away from the middle, the speed and therefore kinetic energy will grow. So that's stable and unstable equilibrium. We've got one more to talk about. Neutral equilibrium. All neutral equilibrium is it's like an object on a flat surface. It's not one way or the other. So in terms of our force diagrams, we're not going to be dealing with that at all, because you're not going to get any curves from those force diagrams. It's just neutral, like Switzerland. Okay. The last thing I want to mention before we wrap this up has to do with planet and asteroid problems, because you'll see one or two of these in this chapter. They'll become more apparent in some of the later chapters, but we just kind of dip our toes into this right now. So for planet and asteroid problems, there's a couple things you need to be aware of. If you're dealing with these, you're not on Earth's surface anymore. And if you have to take potential energy into consideration, potential energy is not just going to be mgy, because the g in that equation assumes you're on Earth's surface. That 9.8 gets lower and lower as you get further and further from the surface of the Earth. So no longer can we use that if we're dealing with these objects that are far away from the Earth. What we have to use for potential energy now for that is this equation. And it's still gravitational potential energy, but because it's such a fancy equation, I actually put the capital G next to it. But it does mean the same thing as the other one. It's just more specific. So that's going to be equal to negative GMM over R. And I just want to make sure you know what each of these letters mean, and then I think we can call it a day. So G is a gravitational constant. It is in the front of your book, or you can just memorize it. It is 6.673 times 10 to the negative 11th. And there's a lot of funky units on it afterwards, too. But that's what that value is going to be equal to. It's a gravitational constant that has to do with how strong gravity acts, believe it or not. And then we've got these two m's here. The big M is the mass of whatever planet it is, or star, that's providing the gravity in your problem. And you can find the mass of the planets and the sun in the back of the textbook. So check that out. You want those masses in kilograms, obviously. Little m is the mass of the little mass. It might be an asteroid, it might be a satellite, a little rock that's coming towards Earth or something like that. So little m is the little mass. Now, the most important part of all this is actually what this R is equal to. This R is very important, and it's the source of most issues with these problems. This R is not equal to a radius, and it's not even really equal to a specific distance from a planet's surface. This is the distance from the little mass to the middle of the big mass. So if you've got a problem where maybe this is the planet that you're looking at, and this is a little asteroid headed towards it, maybe they say that this distance right here is equal to 1,000 kilometers. If that's what they give you, this number is not the R value. What you would need to do to get that R value is you need to take the radius of this planet into account. And so in this case, it's going to be 1,000 kilometers plus whatever the radius of this planet is. And all those values are in the back of the book for you as well. So make sure you're aware of that. And you'll want to convert that to meters too, of course. We want to stay in SI units for this. And that about does it for energy and work. See you guys later. And actually, before, I want to just mention real quick too, for these problems, when you're dealing with them in energy, everything that I've mentioned already still applies. So, because we're dealing with a gravitational force here, energy is conserved. So, original energy maybe is original gravitational potential plus original kinetic, and that's equal to final gravitational potential plus final kinetic. So make sure that you know that this is not something that's supposed to be extra difficult. You still use the same energy equations. The only difference is you've got a different expression for your gravitational potential energy. That's all. So now we're done. I promise.